My name is Barbara Sherwood Lollar, and I'm a professor of earth sciences at the University of Toronto in Canada, where I do research on the intersection of water and life in the deepest and most ancient rocks of the planet. On November 9th, 1989, I was actually putting the final touches on my PhD thesis. The first time that I've begun to work in this area, doing work throughout the world, particularly in Canada and Finland, in some of the deepest mines on the planet. There, the presence of salty waters had been something that miners around the world had been aware of for more than 100 years, but had somehow flown under the radar of the scientific community until that time. As a child, I was raised on a steady diet of books by Jules Verne and others who were writing about exploration, and these ideas of exploration and code breaking fascinated me. When I became a scientist, I didn't really see any connection to those earlier childhood fascinations. But later, as we began to go into parts of the planet, I began to realize that that exploration dream was in fact still a part of the science that I was undertaking today. As we began to discover flowing water older than anyone had ever thought possible, and life in the deepest, darkest parts of the planet where we had not imagined it exist, I realized that science today is still very much a journey of exploration and discovery. And in fact, that's one of the most exciting aspects of our work that continues to keep us engaged and passionate about moving forward. My title is Breaking the Wall of the Deep Planetary Subsurface, because what we're really doing is challenging the paradigm that we humans have about where we find life on our planet. As human beings, we're really wedded to the image of the pale blue dot, the idea that life on our planet is a thin veneer on the surface of the planet only, primarily because, of course, we think of life as being intimately connected with its need for energy from photosynthesis. The first break or crack in the wall of that paradigm actually took place in my lifetime. Towards the end of my high school years in the late 1970s, as deep research submarines were investigating the spreading centers on the ocean floor, as they looked out of their portholes, they saw not only the rocks and magma that they'd come to look at those spreading centers, but also the surprise of life, such as they had not seen it before. Giant tube worms, clams the size of dinner plates. And they eventually discovered that the base of this deep subsurface ecosystem were microorganisms, but not microorganisms drawing their energy from photosynthesis, microorganisms drawing their energy from chemosynthesis, the chemistry of water-rock reaction. And in fact, we refer to these organisms now as chemolithotrophic organisms, literally chemistry and rock-eating organisms. And it changed our understanding of how life could sustain itself in the deep, dark parts of the planet, far from the sun's energy. Nonetheless, over the next decade or so, we still kind of had the idea that this kind of life was associated only with certain special places, where there were high temperatures, hot springs, hot vents. Our work, along with teams of microbiologists around the world, was to discover that these processes of water-rock reaction that can sustain these rock-eating microbes can actually take place in low-temperature environments as well, and that we can find this kind of life deep in the subsurface of the continents, even 2, 3, and 4 kilometers below the planet's surface. This changed the nature of how we think about the planet, to understand that it's a planet that can be almost entirely inhabited deep down into its crust. The challenges continue in terms of our research in this area. How much of this deep subsurface life exists? What controls its distribution and where it colonizes the subsurface? How is it the same or different than microbes that we find on the surface of the planet? And in particular, how long can life be sustained in the deep interior of a planet cut off from the surface photosphere? The insight and innovation in our research is that it's not enough to just investigate the microbial life in the subsurface itself. We need to understand the environmental context for that life. Intuitively, I think we all understand the idea that life needs water to survive. And so indeed, that is our focus. And by studying the water, we provide important constraints and insight into the nature of subsurface life. First, for example, it's extremely important to understand the chemistry of the water, the distribution of electron donors and electron acceptors and nutrients that indeed provide the energy to sustain these subsurface microbial metabolisms. Secondly, it's extremely important to understand the age of the groundwaters, their residence times, because that provides us with important information about how long these microbial communities may have been isolated in the subsurface, how long they might have been isolated one from another, or indeed, in some cases, whether or not a microbial community in fact still retains a connection to the surface hydrologic cycle. Think back to your school days and what you learned about the hydrologic cycle. Typically, when we portray the water cycle, we portray it as a continuous loop, a system in which rainfall, rivers, and oceans percolate into the subsurface, but then inevitably all that water at some point returns, and indeed the entire thing is seen as an interconnected system. Our work has begun to break that image right open, because in fact we've discovered in some places, particularly in the deep ancient rocks of the planet, such as on the Canadian Shield, or Finland, or South Africa, we actually find deep groundwaters that have residence times on the order of hundreds of millions, or even more than 1 billion years. Waters that are essentially isolated from the modern hydrologic cycle and represent a distinct component of what we're calling the hidden hydrogeosphere. Within those deep waters, then, they actually form a type of time capsule in which we can begin to investigate the nature of the water and the life that may have been isolated from the surface on these kinds of immense timescales. The really sustaining and exciting thing about this research is that it has both very fundamental and very practical implications. At the fundamental level, it tells us about the intersection of life, water, and the evolution of a planet. In that sense, our work is indeed an analog for the investigation of fact of life on other planets as well. What many people don't know is that Mars is in some way Earth's evil twin. About 4 billion years ago, just around the time that life arose on our planet, on Earth, Mars was in fact a much more habitable planet. It was warmer, wetter, it had an atmosphere, and if life arose on our planet at this time, it's statistically possible it might have arisen on Mars as well. But in the intervening time, Mars has undergone a major planetary transition. It has lost its atmosphere, lost its surface water, and turned into a cold, dry desert, such as we know it today. If life ever arose on the planet, signs of that life, or even remnants of that life, are thought to only likely persist in the deep subsurface of the planet. So investigating the ability for life to survive in the deep parts of our planet on geological timescales provides us with very fundamental information about thinking about how to explore other planets in the solar system like Mars or the moons of Jupiter and Saturn. On a practical level, our work involves understanding the very nature of water on our planet and its intersection with life. And what's fascinating is that, in fact, even on planet Earth, we still do not have really good estimates on the amount of water resources that we have access to on a planetary scale, on a national scale, or even on a local scale. There are substantial questions about the quality of water. There are questions about the impacts that we, with our human activities, have on that water, either due to agriculture, due to things like fracking, or due to waste disposal. As climate continues to change the weather patterns and the distribution of water on our planet, these questions become even more important to understanding that precious interaction between water, life, and the evolution of a planet's atmosphere. What do these investigations of subsurface microbial life mean for our understanding of the origin and evolution of life? Is it possible that life arose not in one of Darwin's warm little ponds on the surface of the planet, but in fact in a warm little fracture in the subsurface? What do these studies tell us about how long life might persist in the subsurface of the planet if the atmosphere or surface of the planet becomes uninhabitable? And in that sense, then, what do all of these studies tell us about the potential for finding either signs of past life or, in fact, extant life on other planets and moons in the solar system?